Chemistry is the exploration of matter. It investigates its properties and how it changes. Everything around us, from the air we breathe to the food we consume, is composed of chemicals. Understanding chemistry allows us to grasp the world at its most basic level. Chemistry is crucial to many sectors. These include healthcare, agriculture, and manufacturing. It plays a key role in developing new technologies and addressing global challenges. By understanding the principles of chemistry, we unlock limitless possibilities for innovation. Imagine a world devoid of chemistry. We wouldn't have life-saving medications. We wouldn't have fertilizers to cultivate food. We wouldn't have the materials to construct our homes or power our cities. Chemistry is not merely a subject confined to textbooks and laboratories. It's the language of the universe, and once you begin to understand it, you'll see its marvels everywhere you look. Let's delve into the heart of matter atoms. Atoms are the smallest unit of an element. They're incredibly tiny, yet they hold the secrets to an element's identity and behavior. Atoms are composed of three primary particles: protons, neutrons, and electrons. Protons, positively charged, reside in the atom's nucleus, its central core. Neutrons, with no charge, also reside in the nucleus, providing stability. Electrons, negatively charged, orbit the nucleus at high speeds. They occupy specific energy levels, like planets orbiting a star. The number of protons, neutrons, and electrons determines an atom's properties. For example, the number of protons, also known as the atomic number, defines an element. Carbon has 6 protons while oxygen has 8. The arrangement of electrons dictates how an atom interacts with others, forming the basis of chemical bonds. The periodic table is a cornerstone of chemistry. It's a chart that organizes all known elements based on their atomic number and chemical properties. This arrangement reveals patterns and trends that help us predict how elements will behave. The periodic table is organized into rows called periods and columns called groups. Elements in the same group share similar chemical properties. For instance, group 1 elements, the alkali metals, are highly reactive. Periods, on the other hand, represent increasing atomic number. As you move across a period, you'll observe gradual changes in properties, such as electronegativity and atomic radius. This systematic arrangement makes the periodic table a powerful tool for understanding the elements. The periodic table is not just a static chart, it's a dynamic tool that continues to evolve as new elements are discovered and our understanding of chemistry deepens. It's a testament to the power of human ingenuity in organizing and making sense of the vast diversity of matter in the universe. Atoms are rarely found in isolation. They interact with each other, forming bonds to create molecules and compounds. Chemical bonds are the forces that hold atoms together, and they are the basis of all chemical reactions. Two primary types of chemical bonds are ionic and covalent bonds. Ionic bonds occur when one atom donates an electron to another, creating oppositely charged ions that attract each other. This is like a game of give and take in the atomic world. Covalent bonds, on the other hand, involve the sharing of electrons between atoms. This sharing creates a stable arrangement where both atoms achieve a full outer shell of electrons, satisfying their need for stability. Chemical bonds determine the properties of molecules and compounds. For example, water, H2O, is a polar molecule due to the unequal sharing of electrons between oxygen and hydrogen atoms, giving it unique properties like high surface tension and the ability to dissolve many substances. Section 5. Chemical reactions, the dance of atoms and molecules. Chemical reactions are all around us. They're the processes by which atoms and molecules rearrange themselves, breaking and forming bonds to create new substances. From the burning of fuel to the digestion of food, life itself is a symphony of chemical reactions. In a chemical reaction, reactants are the starting materials, while products are the substances formed. The law of conservation of mass states that matter cannot be created or destroyed, only transformed. This means that the total mass of reactants equals the total mass of products in a chemical reaction. Chemical reactions can be exothermic, releasing energy into the surroundings, or endothermic, absorbing energy from the surroundings. Photosynthesis, for example, is an endothermic reaction that harnesses energy from sunlight to convert carbon dioxide and water into glucose and oxygen. Understanding chemical reactions is crucial in many fields, from developing new materials and medicines to addressing environmental challenges. By manipulating the conditions of a reaction, we can control the types and amounts of products formed. Section 6, Acids, Bases, and the pH Scale, a balancing act. Acids and bases are two important classes of chemicals. Acids are substances that donate protons, or H+, when dissolved in water, while bases accept protons. The pH scale measures the acidity or basicity of a solution, ranging from 0, which is the most acidic, to 14, the most basic. A pH of 7 is considered neutral, like pure water. Acids have a pH below 7, while bases have a pH above 7. The pH scale is logarithmic, meaning that each whole number change represents a tenfold difference in acidity or basicity. Acids and bases play vital roles in many biological and industrial processes. For example, our stomachs produce hydrochloric acid or HCl to aid digestion. Baking soda, which is a base, is used in cooking and as an antacid to neutralize excess stomach acid. Maintaining the proper pH balance is essential for life. Enzymes, the catalysts of our cells, function optimally within a narrow pH range. Buffers are solutions that resist changes in pH, helping maintain a stable environment for these vital processes. Section 7, States of Matter, Solid, Liquid, Gas, and Beyond. Matter exists in different states: solid, liquid, gas, and plasma. The state of matter is determined by the arrangement and motion of its particles. Temperature and pressure are the key factors influencing these states. In a solid, particles are tightly packed and vibrate in place. They have a fixed shape and volume. In a liquid, particles are more loosely packed and can move around. They take the shape of their container but have a fixed volume. In a gas, particles are far apart and move freely. They have no fixed shape or volume and expand to fill their container. Plasma, the fourth state of matter, is an ionized gas found in stars and lightning. Understanding the states of matter and their transitions is crucial in many areas, from designing materials with specific properties to predicting weather patterns. For example, the water cycle, involving the continuous evaporation, condensation, and precipitation of water, is essential for life on Earth. Section 8. Stoichiometry, the recipe for chemical reactions. Stoichiometry is the branch of chemistry that deals with the quantitative relationships between reactants and products in chemical reactions. It's like a recipe book for chemists, providing the precise amounts of ingredients needed for a desired outcome. Using balanced chemical equations, we can determine the mole ratios between reactants and products. A mole is a unit of measurement for the amount of a substance, just like a dozen represents 12. It allows us to relate the macroscopic world to the microscopic world of atoms and molecules. Stoichiometry is essential in many practical applications. For example, in the pharmaceutical industry, it's used to calculate the precise dosages of drugs. In environmental science, it helps determine the amount of pollutants released into the environment. By understanding stoichiometry, we can predict the amount of product formed from a given amount of reactants, determine the limiting reactant that controls the reaction, and calculate the percent yield of a reaction, which measures its efficiency. Section 9. Thermochemistry. The heat is on. Thermochemistry is the study of heat changes associated with chemical reactions and physical transformations. It helps us understand whether a reaction will release heat, which we call exothermic, or absorb heat, known as endothermic. Enthalpy, abbreviated as H, is a state function that measures the heat content of a system at constant pressure. The change in enthalpy, or DH, during a reaction indicates whether it's exothermic, where DH is less than 0, or endothermic, where DH is greater than 0. Exothermic reactions release heat into the surroundings, like burning wood. Endothermic reactions absorb heat from the surroundings, like melting ice. Thermochemistry helps us predict and control these energy changes. Thermochemistry has numerous applications, from designing efficient energy storage devices to understanding the energy flow in biological systems. For example, cellular respiration, the process by which our bodies extract energy from food, is a series of exothermic reactions that release energy to power our cells. Section 10. Conclusion. Chemistry is everywhere. Chemistry is the study of matter and its transformations. From the smallest atoms to the largest stars, chemistry governs the universe. Understanding the basic principles of chemistry empowers us to comprehend the world around us and develop solutions to global challenges. We've explored the building blocks of matter, the interactions between atoms and molecules, the nature of chemical reactions, and the role of energy in chemical processes. Chemistry is not just a subject confined to textbooks and laboratories. It's the language of the universe, and once you start understanding it, you'll see its wonders everywhere you look. So, embrace the power of chemistry and continue to explore the fascinating world of atoms, molecules, and their endless transformations.